This lecture is intended to immediately follow up my opening demonstration on resonance. This lecture is intended for Physics AB. In my demonstration, I took a simple pendulum and I applied an external driving force. That driving force was supplied by means of some rubber bands, resulting in what are referred to as forced oscillations. And then, as we saw, the frequency of my hand moving back and forth, the driving frequency omega, well, if it matched up with the natural frequency of the simple pendulum, then large amplitude oscillations occurred. That condition is referred to as resonance. We say that the oscillator is resonating. We seek to understand why that happens here in this lecture. Okay, now when I describe this mathematically, however, I'm going to describe it in the context of a mass attached to a spring, even though I used a simple pendulum in my demonstration. Okay, so what we do here is we apply an external driving force to a simple harmonic oscillator. And here's then mathematically how we describe that external driving force. This is the force that I supply by means of the rubber bands as a function of time. Okay, as you saw in the demonstration, I was oscillating my hand back and forth, hence the cosine. But the cosine here is in terms of the angular frequency of my hand moving back and forth, not the natural frequency of the oscillator itself. So omega is the driving frequency of my hand. And omega naught, which is equal to the square root of k over m when talking about a mass attached to a spring, this right here is the natural frequency of the oscillator. And then as we saw in the demonstration, when the driving frequency of my hand moving back and forth matches up with the natural frequency of the oscillator, large amplitude oscillations occur. That situation is referred to as resonance. Okay, now when we take into account the external driving force, when we apply it to a mass attached to a spring, this then results in the following differential equation from F equals ma. We first of all have the spring force, and then I add to that this driving force. This then gives us the net force mass times acceleration. So this is a pretty complicated differential equation because as the position of the oscillator is continuously changing, and as I'm moving my hand back and forth, the acceleration of the oscillator is continuously changing as well. What I'm going to do is quote to you the solution to this differential equation. Of course, in this algebra-based course, we don't do any of the calculus, but then I'll explain why the solution works the way it does in the context of the demonstration. Okay, the solution to this differential equation is a position equation that's written out like so. This is the position of the forced oscillator. It's once again just a cosine curve. The cosine curve, however, is in terms of the driving frequency of omega of my hand moving back and forth, not the natural frequency of the oscillator itself. The amplitude is referred to as capital A naught, and this is what we're most interested in. Through the calculus that I'm skipping, the amplitude ends up being a function of the driving frequency, where A naught is a function of omega. The expression itself that comes out of the calculus that describes the amplitude as a function of omega looks like this. Once again, this comes from the calculus that I'm skipping over. This expression here. Now the expression is written the way it is. The parentheses here is squared, and then we take the square root of it just to get rid of any negative signs associated with the denominator. For example, if the driving frequency is greater than the natural frequency, then here in the parentheses you would end up with a negative number, which doesn't really mean anything in this context when talking about the size of the amplitude. So then therefore we get rid of the negative sign by squaring and then taking the square root as we've done. Once again, this expression comes directly from the calculus and setting up and solving the differential equation itself. The easiest way to understand the behavior of this expression and how it relates to the demonstration, however, is to actually just graph it out. So here's a graph of the amplitude as a function of the driving frequency omega. And then right here we'll say is the natural frequency omega naught of the oscillator. And now let's see mathematically how this behaves. So for example, let's say that the driving frequency is small. So my hand is moving barely back and forth like so, as I did in my demonstration. When you watch that demonstration, you'll note that the amplitude of the motion is small, like so. And then let's take a look at the far right-hand side of the graph, where the driving frequency of my hand back and forth is a large number. So I'm rapidly moving my hand back and forth, as you saw me do in the demonstration. When I did, the pendulum was barely jiggling around. Once again, the amplitude is small, like so. However, take a look at what happens when omega is equal to omega naught. When these two quantities are equal to each other, you end up with 0 in the denominator of the expression, and then therefore the amplitude is undefined. In other words, you literally end up with an infinitely large amplitude. There's an asymptote on this graph, like so. So on this side of the graph, as the driving frequency of my hand approaches the natural frequency of the oscillator, then the amplitude of the oscillation gets large, and then it comes down on the other side like so to complete the graph. So what you're looking at here then is literally an infinitely large amplitude when the driving frequency omega matches up with the natural frequency omega naught. The oscillator is resonating. Now, of course, in the actual demonstration, the amplitude of the pendulum wasn't infinitely large. So then therefore, what really happens? Well, what really happens is to take damping into account. Because remember that there's no such thing as an SHO, there are only DHOs. So if you take damping into account, it changes this equation a little bit, and it changes this graph as well. Here's what happens when you take damping into account. So if we take damping into account, the function that describes the amplitude as a function of omega is the following. There's an extra term underneath the radical sign. That radical sign, that extra term rather, underneath the radical sign, has the coefficient associated with damping that occurs within it. What this then does to the asymptote on the graph is it changes it from an asymptote to instead a finite-sized resonant peak, as we say, associated with the amplitude. So here's then what happens to the graph. So right here is where approximately omega is equal to omega naught. Through the calculus, they're actually not quite exactly the same, but right around that value, you then end up with a finite-sized amplitude like so, that is really large. This right here is referred to as a finite-sized resonant peak. So that's what you're seeing in the demonstration involving my pendulum. It's a forced damped harmonic oscillator, and when the frequency of my hand going back and forth matches up pretty closely with the natural frequency of the pendulum itself, then large amplitude oscillations occur. Now, there are really no problems associated with resonance per se, because resonance is just a specific physical case, but there's a number of demonstrations that I perform after this video for you to take a look at as well.